Alrighty. So, there we go. This is take 2 of week 7 for the problem session therein. And I'm going to start off with problems from the homework. And the first one that was asked about was to do one like number 3 on homework 6. And there are a couple of different ways we could go about solving this one. What the question asked is to find f prime of x and f prime of 4. And so that means first off we have to take the derivative. And that's the thing that I was saying you could do multiple ways. Right? One way is we could look at this and say, okay, f of x equals 6 times ln of 5 plus ln of x. So we could use our log expansion rules. And then when we take the derivative of this, right, we pull the 6 out front using the constant multiple rule. The derivative of a constant is just 0. And the derivative of ln of x, we learned in one of these sections, is 1 over x. So that becomes 6 over x. The other way to do this, if you don't want to use your log rules, is to use the fact, let me put it up here, the derivative of ln of g of x is equal to g prime of x over g of x. So that's another rule that we learned in this section. It's basically combining this rule that we used here and the chain rule. So we could use that to say, to go from this guy, again, constant multiple rule pulls that 6 out, and then the derivative of 5x is just 5, and then 5x itself is what goes on the bottom, right, using this formula right here. The 5 and the 5x cancel, and again, we get 6 over x. Right, so there's those two different ways to do it. Both of them get the same thing, which is very good. If they got a different thing, we'd be in trouble. So we have f prime of x equals 6 over x. And that means that f prime of 4 is what we get when we plug 4 in. So we get 3/2 there. Right? Number 4, which is the next one that people asked about, is very similar, except only one of these ways works. Right? When we have just a polynomial here, right, if what's inside the log is polynomial, you can always use, or rather, not even a polynomial, a monomial. Then you can use log rules to expand it and then just use the basic derivative of logs. If, as in this problem, you have inside the logarithm a trig function, well then you have to use this method. Right, this one up here. So this one wants the second derivative, so it's a little bit different in that sense, but it's using that same rule. Right? So first, if we're going to find the second derivative, we got to find the first derivative. And this 11, we use the constant multiple rule to pull it out. And the derivative of ln of a function is the derivative of that function. So the derivative of cosine is negative sine, divided by that function, just exactly as it was. So we pull that negative out, and we realize that sine divided by cosine is tangent. Right? Now, if we don't realize that, it's not going to be too big of a problem. You're just going to wind up using the quotient rule to get the second derivative. But it's a good idea to get practice in recognizing that sort of thing, because finding the second derivative is a lot easier if you don't have to use the quotient rule and just use our trig derivatives to know that the derivative of tangent is secant squared. And that's what the question was asking for. So the next one is a twofer, because people asked about 7 and 8. And those two problems are exactly the same problem with slightly different numbers. So if I'm going to do another version of that problem with slightly different numbers, I just get the same problem for both of them. So we have a similar start. And in fact, it's going to be a very similar thing to what we did on the first one. So in this one, we could absolutely do what we did. Whoops, not of 3, just of x. We could absolutely do what we did on number 4 and this version here, and use the derivative of log of a function thing to say that it's the derivative of this guy divided by that guy. We could absolutely do that. But the problem there being is that I don't want to find the derivative of that nonsense. That's a giant ass polynomial. I got to use like the chain rule multiple times. I got to use the product rule multiple times. Either that or I have to multiply all those things out, and that just sounds like no fun. So while this one you can use the rule that we did here, it's going to be a lot easier to use the rule that we did here. And in fact, this problem is setting you up to get some practice in logarithmic differentiation. And the entire point of logarithmic differentiation is that I don't want to find the derivative of this nonsense. So let's not do that. And instead, let's use our skills at expanding logarithms to rewrite this. So first off, we break up all the products into sums. And then we pull we use the, I guess it's the power rule for logarithms to pull those powers out. And that's as far as we can expand that logarithmic expression, right? So we notice that not all those logarithms are just of x. So we are still going to have to use this rule that we have up here with this exceedingly splotchy star that I put up there. But it's going to be with things that are a lot easier to take the derivative of. So when I want to take the derivative, this one, constant multiple pulls that 3 out. Ln of x is just 1 over x. Constant multiple pulls that 5 out. Then we put the derivative of this guy, which is just 3, divided by that guy. Constant multiple pulls the 7 out. And we put the derivative of this guy, which is 3x squared, divided by that guy. And that's what we got. That's our derivative. You can simplify it if you really want to, but I wouldn't recommend it. This is a perfectly acceptable way to leave the final answer for a problem like this. So the next one, check real quick. Okay, good. So, like number of 10, I'm not going to write out the whole word problem was there. I'm going to sort of highlight the phrases that are important. So we have the number of items X depends on price P by X equals 50,000 divided by the square root of 2p plus 3. So I should say these next 3 problems that we're going to do from the homework are all related rate problems. right? So this sentence is important because it names all of our variables, right? That's one of the big steps for related rate problems. And it gives the relationship between the variables that we have. So we have a variable x, we have a price p, and we have a relationship between them. And we have that they are increasing the price by $3 per month. Right, so that's the next sort of important sentence. This tells us that all of our functions are functions of t. So, or all of our variables rather are functions of t. So the price is increasing with time. So it's a function of t. X depends on the price, so it's a function of t. So we know that we're dealing that all of these are functions of t, right? So we have x is some function of t, p is some function of t, and specifically we know that dp dt, so the derivative with respect to t, right? So this increasing means it's changing over time, and it's changing by 3 exactly. This first sentence is how we find the relations and name the variables. This second phrase right here helps us gather all the things that we know. And then the last sentence, this is important, is the one that actually asks the question, is find the rate, the revenue is changing when the company is selling at $100 each. Right, so what we can get from this is that our question is, what is d revenue, dt, right? Rate tells us we're looking at a derivative, and the only other information we have about derivatives is with respect to time. And this also tells us that we specifically care about it when p equals 100. Now, we can't plug that into anything yet, right? Anytime you have just the straight value of a variable, you plug that in at the very last step, because any derivatives we take aren't valid if you've plugged something in yet. So at the very least, even if you don't do it at the end, you have to do it after you take the derivative, right? So this requires one bit of extra knowledge about the vocabulary in this problem, and that is that revenue as a function of t, or revenue in general, is always the number of items you're selling times the price you're selling them at, right? If you sell 5 things for $20 each, your revenue is $100. If you sell 20 things at $2 each, your revenue is $40, right? So we want to find dr dt, right? So this is dr dt, right? And looking at it right off the bat, that's going to be the product rule, right? So dr dt is going to be x times dp dt plus p times dx dt, right? And we know at least 2 of those things, right? We've taken the derivative, so now we can plug stuff in, right? We know that dp dt is 3, and we know that p itself is 100. So we need to figure out the other 2 things, right? And so to figure out dx dt, right? That's going to be the derivative of this guy. So it's going to be d dt of 50,000 square root of 2 pt plus 3. So I'm going to rewrite that because I don't really like the quotient rule myself as 50,000 times 2 p of t plus 3 to the negative 1/2, right? And that's going to let me use the power rule and the chain rule and not worry about the quotient rule because that doesn't sound like too much fun, right? So we're going to bring that power down, negative 1/2. Constant multiple rule says that 50,000 sticks around. This becomes 2 pt plus 3 to the negative 3/2, right? The power always goes down by 1. But then we have to multiply by the derivative of 2 pt plus 3. All right, so let's see. This combines to be negative 25,000 2p of t plus 3 to the negative 3/2. And the derivative of that with respect to t is 2, because the constant multiple rule, dp dt, because that's what we get when we take the derivative of p, and the 3 disappears. Whew. Okay. But we don't care about this function in general. What we care about, so the thing we're going to plug in here, right, is what we get when we fill stuff out, right? So we're going to get, let's see, that bumps back up to negative 50,000 here. P of t is 100. And dp dt is 3. So we get negative 150,000 times 203 to the negative 3/2. Whew. And lastly, we need to figure out what x is. So this is going to be what we put where that box is. X, we have that x equals 50,000 over root 2p plus 3. And, whoops, we know that we want p to be 100. So that's going to be what we'll plug in for that 0 there. So our final answer for dr dt, and one notation that I haven't used a whole lot, but we want this specifically at p equals 100, right? We don't want the generic derivative. We want it at a specific point. So this is going to be 3 times x at that specific point. Plus 100 times dx dt at that specific point. So we get this guy. And usually for this type of problems, we want some sort of approximation, right? We want some sort of decimal form, probably to 2 decimal places, since this is a money problem. And our money is standardly in units of pennies, so we often go out to 2 decimal places. But you'd get that by plugging this number into your calculator and letting it round for you. Right? But that's the process that we sort of get there. Right? Most of these sorts of problems are just keeping track of everything that you're doing. So we got a couple more on board. So let's do some more related rates. So like number 11. Okay, just checking. Okay, so at noon, ship A is 30 nautical miles due west of ship B. Ship A is sailing west at 15 knots. And B is sailing north at 20 knots. Right? How fast is the distance changing at 4 p.m.? Right? So, this is a related rates problem, we can tell because of the homework that we're on. Also, we have how fast, which is what tells us that it's a rate. And the related part comes from the fact that we don't have a function to take the derivative of to figure out how fast. At least in the problem is given. Right? But what do we know? Well, we've got sort of a picture going on here. Right? So, ship A at noon and ship B at noon are here. And there's 30 miles between them. Right, then ship A starts moving at 15 knots. And ship B starts moving at 20 knots. And the distance between them at any given point is that, and that looks like a very handy geometrical figure that that we should know some stuff about, right? So just to have variables for these things, let's call this guy X and this guy Y. It doesn't really matter what variable you choose. It can be A and B if you want to harken back to the Pythagorean theorem that we're going to be using here in a second. You can call this C if you really want to for that same reason. I'm choosing D because it's the distance. But that's all up to you. The problem doesn't tell you what they have to be named. So here we have D squared equals X squared plus Y squared. And, we could do a couple different ways to figure out how this goes. We could, for instance, figure out what X and Y are. Right? So X is always going to be, there's always going to be that 30. Oh, before we do that real quick, actually, I almost forgot. Is that this how fast is also telling us this is going to be a derivative with respect to t problem. Right? So there's going to be a time involved in there somewhere. Also, the fact that we were given speeds here also tells us that we know some things about dt. So, since we have things about noon and then 4 hours later, and knots are miles per hour, right, we're going to let t equal the time in hours since noon. Right, so this tells us that we care about t equals 4 eventually. So, one of the ways we could go about this is figuring out what X and Y are. Right, so X, there's always going to be that 30 that we started out with here. But then every hour it gets past noon, we're going to add another 15 to it. So another way to say that is 30 plus 15t. And Y, there's nothing here to start off with. This is completely going to be based on how fast B is moving. So we get 20t there. And so one thing that we could also note just from this thing is that even before we figured this out, we could have figured out that dx dt is going to be 15 and dy dt is going to be 20, right? For the same reason that in this problem up here, we knew immediately that dp dt was 3. right? Because we were told how fast the price was increasing. So here we're told how fast x and y are increasing. So even before we got these these functions, which means that it's pretty easy to find these derivatives, we could find the derivatives on their own. That's actually given to us in the problem. In this case, we have to do a weird sort of thing of figuring out the function from their derivative. All right, so we have all of that set up. Let's see, is there anything else we need to set up? I think we're pretty good there, right? Because if we want to know how fast the distance is changing, then we actually have this weird thing where we're looking for dd dt. So dd dt is going to be, we're going to have to use the chain rule on this guy, right? So that's going to be 2x, or rather the generalized power rule, which is the chain rule and the power rule together. So it's going to be 2x times dx dt, right? Because if we were just taking the derivative with respect to x, that would be 2x, and we'd be done. But since we're taking the derivative with respect to t, we have to use the chain rule because this base is not just t, it's a function of t. Right? Similarly for over here, 2y we would be done if we were taking the derivative with respect to y, but since we're taking the derivative with respect to t, we also have to get the derivative of the inside there. All right. So this is 2 times 30 plus 15t times 15 plus 2 times 20t times 20. Oh, and I've messed up a little bit here. Right? Maybe we could figure it out, but this piece here, this is not equal to d, this is equal to d squared. So the derivative of d squared dt is equal to this guy. So let's go ahead and simplify this out. Let's see, we've got 900 plus 450t think I got that right. Yeah. Plus 800t equals 900 plus 1250t. Right? But we also know that d squared dt, in the exact same way that this one and this one worked, right? That's going to be 2d, and that would be it if we were taking the derivative with respect to d. But since we're taking the derivative with respect to t, we have to take the derivative of the inside there. Now, this is what we actually want, right? That's what's going to tell us how fast the distance is changing. So we know that the derivative of the distance with respect to time is going to be 900 plus 1250t all over 2d. So we know what t is supposed to be. So that's gonna, oops. When we plug in t equals 4, we get 900 plus 1250 times 4 divided by 2. And here's where things get tricky, because we need to figure out what d is at t equals 4. So x of 4 is going to be 30 plus 15 times 4 equals 30 plus 60 equals 90. Y of 4 is going to be 20 times 4, so 80. So we know that d squared, or d of 4 squared, is going to be 90 squared plus 80 squared. So d of 4 is going to be the square root of 8100 plus 6400 14500. And we can plug that in here. And again, this would be a good one to throw in your calculator at this point. Maybe just simplify the top if you want to get an exact answer. Do pay attention, especially on the exam that's coming up. The calculator, or the computer, doesn't mind rounded answers because it's going to round everything in its brain anyway. I will often ask for exact answers, so make sure to pay attention to the instructions, and when it asks for an exact answer, don't give me some decimal approximation. Give me the exact answer. All right. But this is what we get for our rate of how fast the distance is changing. Right. And one more related rates problem from the homework. Let me check on this. Okay, we're still good. So again, I'm not going to write out the whole word problem, but we're going to say we have a 10-foot pole, a 5-foot woman walking away at a speed of 6 feet per second. And we want to know how fast is the tip of her shadow moving when she is 40 feet away from the pole. Right? So, how fast means we're dealing with a rate. All of our things are in time, both fast and per second. So t is going to be seconds. It's not going to matter too much in this problem, but it's always a good thing to note down. So we have a light pole, a lamppost here that is 10 feet tall. Right, and we have a woman who is moving away from the lamppost, who is 5 feet tall, and this is the ground she's walking on. One of the things that you sort of have to know going into these problems, which you can get from doing the practice or reading the book or having it looked at, or I think there was a video to go along with this one, is that shadows, okay, we're going to pretend like that's a straight line. I can even use my drawing program to cheat. Shadows obey this rule. So if you have a light cast from up here and you draw a line from the light, hit the top of the thing casting the shadow's self, and draw a line till it hits the ground. That's how long the shadow is. Right? So the rate of change of this distance is what we want, right? Because this is the tip of our shadow, and how fast that number is growing is telling us how fast the tip of her shadow is moving. So once we have this labeled, the problem is asking what is dy dt when something, we don't have a name for it yet, is 40, right? But we figured out that we need a name for something, so let's call that x. And then note that that has to be x now. Right? So we know that we need to be able to talk about what happens when the woman is 40 feet away from the pole. So that means we need a variable that has to do with that, right? So that's how I knew that I needed to name that x. And then what we can do here is notice that we have a set of similar triangles, right? So this big triangle, this one here, is a similar triangle to this smaller triangle made here. And that's going to be the case whenever you take a triangle and draw a line part of the way through that touches the bottom of the triangle and the hypotenuse of the right triangle, then you're going to have a pair of similar triangles. So what that tells me is that, let's see, 10 divided by 5. So if we take this side, the ratio of that and that side is going to be the same as the ratio of this long piece here, which is y, divided by the length of this piece here, which gives us a bit of a moment's pause because we don't have a name for that yet, right? But we do see that if we take y and we subtract off x from it, this piece is exactly what's left, right? What we have here is what's left over to be that side of the triangle, right? So the ratio of the two left sides of the triangle is going to be the same as the ratio of the two bottom sides of the triangle. That's what similar triangles mean. So we can simplify this. We get 2 times y minus x equals y. So we get 2y minus 2x equals y. If I subtract y from both sides and add 2x to both sides, I get that y equals 2x. And that's the relation part of this related rates problem. So now I want to find dy dt. So I take the derivative of the left as dy dt. And then that means I need to look at this guy, right? Constant multiple rule says that I can just pull that 2 out, dx dt. So that means that we need to know dx dt, right? And we have this idea that x is equal to 40, but it turns out that that's not important for this problem. We don't have any x's left over, right? So often you'll be given extraneous information, so it's not something to panic about, right? Just make sure that you didn't lose any x's anywhere, and you're good, right? But we do need to know dx dt, so maybe we want to go back and look at our word problem up here, right? So do we have, what we need to be looking for is anything that tells us the rate of change of how far the woman is from the lamppost, right? And that's exactly what this second half of the first sentence tells us. The woman is walking away from the lamppost, right? So it's going to be a positive change, and it's changing by a flat 6 feet per second. So this is going to be 2 times 6, or 12. Right. Okay, so that's the last of the questions from the homework. So I have a couple from the book that were asked about. So from section 4.2, number 52 was asked about, and that asked to find the max and min of 4 sine cubed theta minus 3 cosine squared theta on 0 to 2 pi. So the way we find maximums and minimums on closed intervals is first we find all the critical points, then we take all of our critical points and the endpoints of the interval, and we plug them into our original function. And we figure out which ones are the biggest and which ones are the smallest. So, to find the critical points, that means taking the first derivative and setting equal to 0. So, the first derivative, we're going to use the chain rule on this first guy here, the generalized power rule, to bring that 3 forward and get 12 sine squared theta. But then, since it wasn't just an x that was being raised to the third, it was a sine theta, we have to then multiply by the derivative of the sine theta. Right? We're going to do the same thing over here. We're going to bring that 2 forward and drop the power down to 1. But then, since it wasn't an x that was being squared, it was a cosine, we need to multiply by the derivative. So we get 12 sine squared theta cosine theta plus 6 cosine theta sine theta. And we want to know when that is equal to 0. Right? So this looks pretty daunting, but there's also some pretty clear factoring we could do. And that's always one of the first things that we want to do when we're setting something equal to 0. Right? So we can pull a 6 out. There's a sine in both of these terms, so we can pull one sine out. There's a cosine in both of these terms, so we can pull a cosine out. Once we pull a 6 out, there's a 2 left there, and there's one sine left over here. But we pulled everything out of that term, so it's just a 1. Right? So now we can pull it out and get that we want either sine theta to equal 0, cosine theta to equal 0, or 2 sine theta plus 1 to equal 0. Sine and cosine equaling 0 are pretty easy. This gives us theta equals 0, pi, or 2 pi. This one gives us pi over 2 and 3 pi over 2. Right, we can do some quick algebra to figure out here we want sine to equal negative 1/2. Right, and that's not going to be too bad because that's one of our standard angles that we should have memorized, one of the angles that shows up on every unit circle. So if you have a unit circle, you can just use that. Otherwise, we need to remember that sine of pi over 3 equals positive 1/2. And sine theta is less than 0 in Q3 and Q4. So we need to take pi over 3 and move it to its reference angles in quadrant 3 and quadrant 4. So quadrant 3 gets us 4 pi over 3. Quadrant 4 gets us 5 pi over 3. All right. So we need to check all 7 of these values, but we did luck out in that the endpoints of our interval are also critical values, right? So we're only going to have to check our critical values because our endpoints are critical values. If they hadn't shown up on the list already, we would have to put them in as well, right? So f of 0 is going to be 4 times 0 cubed minus, so I'm starting off with these guys because for all these guys, we know that sine is 0. So we can always just ignore that term. And whenever sine is 0, cosine is 1. So that's going to make these easy. So that's negative 3. It's going to be the exact same thing for pi because pi makes sine 0 and therefore it makes cosine 1. And it's going to be the exact same thing for 2 pi for the exact same reason. Right? So all those are negative 3. We're going to have a similar pattern for the cosine ones. So f of pi over 2 is going to make cosine 0, right? That's why it's on this list. And whenever a cosine is 0, sine is 1. So we're going to have 4 times 1 cubed minus 3 times 0. Whoops, these should all be squared. Doesn't change anything, but might as well have the correct thing written there. So that's going to be 4. And 3 pi over 2 is also going to be 4 because cosine is 0 at 3 pi over 2, and therefore sine equals 1 at 3 pi over 2. Right. Now, the next two are going to be a little bit more exciting, but not super exciting because of the way things worked out. 4 pi over 3, we know that that's going to give us sine equals 1/2. So we get negative 1/2 cubed minus 3. Now, if sine is plus or minus 1/2, then cosine is going to be, oh, I just realized something. This is not actually going to be positive 1. It's going to be negative 1 there, right? But we cube it, and so, or we square it rather, so it becomes positive, so we still get negative 3 there, right? And I realize that because it's the same thing that's going to come up here. If sine is plus or minus 1/2, cosine is going to be either plus or minus root 3 over 2. And it turns out, because we're squaring the cosine terms, it doesn't matter which one of those it is. Turns out, since it's in quadrant 3 has negative x values, so it's negative root 3 over 2. But that's the same value as we get if it were positive. So this is negative 1/2 is left over here. Minus, well, let me do more steps there. So 4 times negative 1/8 minus 3 times 3 over 4. So we get negative 1/2 minus 3, minus 9/4. 1/2 is 2/4, so this is 11/4. And turns out we get exactly the same thing with 5 pi over 3. Because 5 pi over 3, we know that sine's going to be negative 1/2. Because that's why we're looking at 5 pi over 3 in the first place. And this time, in quadrant 4, cosine is positive. So we get positive root 3 over 2. But since we're squaring it, that's going to be exactly the same. Right, so we'd get 4 times negative 1/8 minus 3 times 3/4. And that's negative 11 over 4. So negative 11 over 4 is slightly more than negative 3. So these are our maxes, or minimums rather. And these are our maxes. Right, because positive 4 is bigger than all those other values. Whew. Okay. So, this, okay, we can maybe fit both of these here. So number 73 from the same problem. This is mostly a conceptual one, so I'm going to do a lot of talking here. But we want to show that the absolute value of velocity is max when the acceleration, which remember is the derivative of velocity, is 0. And we also want to show that the absolute value of the acceleration is maximum when the velocity is 0. Right, and I mostly want to talk about this one, because the other one sort of follows very similarly, the exact same logic, in fact. But if you think about it, absolute value of velocity being maximum means that v of t is either a max or a min. Right? If the velocity is negative there, and the absolute value of it is a maximum, then the velocity actually had a minimum there. And if the velocity was positive, and the absolute value had a maximum there, then the velocity is equal to the absolute value of the velocity, and so you also have a maximum there, right? So this is really just a restatement of saying that a function will achieve a maximum or minimum when its derivative is 0, right? So at those critical points. We don't have a closed interval here, so the only place it could possibly reach its maximum or minimum is when the derivative is 0. And the same concept there, the velocity is not the derivative of acceleration, but I actually forgot an important thing with this problem, is that the position function is sine. So while the velocity is not the derivative of acceleration, the velocity is just a constant multiple of the derivative of acceleration, right? We get that the velocity is equal to a omega cosine of omega t. We get that the acceleration is equal to negative a omega squared sine of omega t. And we get that the derivative of acceleration is negative a w cubed cosine of omega t. So the velocity and the derivative of acceleration, since a and omega are just constants, are going to be 0 at the same place. They're going to be 0 whenever cosine of omega t is 0. So that the second thing that you were trying to show there is actually asking to show the same thing as the first thing in a roundabout sort of way. So let's see if I can fit this last problem in here. This is one for section 4.3, number 7. And it asks us to find C from the mean value theorem for y equals e to the negative 2x on the interval 0 to 3. So the mean value theorem says there is a C such that f of c, whoops, not f of 3, such that f prime of c equals f of b minus f of a all over b minus a. So what we need to do to find this c is figure out all those pieces and plug stuff in. So first, the derivative of f. So that's going to be the generalized exponential rule, I think they call it here. We take the derivative of the exponent, which is negative 2, and then we put the whole function back where it was. Right? It's just the chain rule and the exponential rule here. So the mean value theorem says that negative 2e to the negative 2c equals f of 3 minus f of 0 all over 3 minus 0. So that's e to the negative 6 minus e to the 0 all over 3 minus 0. So we have negative 2e to the negative 2c equals e to the negative 6 minus 1 over 3. I'm going to go ahead and multiply that 3 over. Get negative 6e to the negative 2c equals e to the negative 6 minus 1. Divide both sides by negative 6. All right. We want to get that c out of the exponent, and we do that by taking the natural log of both sides. So negative 2c equals the natural log of e to the negative 6 minus 1 all over negative 6. And then we want to isolate that c, so c itself is going to equal the natural log of e to the negative 6 minus 1 -6 all over -2. Now, there was one other thing that the mean value theorem says that I didn't put down here, is that there's not just a random C, there's a C in between A and B. So just to make sure this is the right one, I went ahead and plugged this guy into my calculator. Got 89.71. That is in between 0 and 3. So this is the correct C that the mean value theorem says exists. Right? Excellent. Made all the use of the space we could. As a reminder, next week the exam goes up, or the exam goes up on Monday. So there is not a problem request this Friday. Instead, you can just post request in the discussion board all week long, and I'll respond whenever I get a chance to. So there won't be one specifically on Friday. There's not one due at all. But if you have questions, there's a discussion board set up to put them on so I can do some responses. I will see y'all later.